Okay, so again, calculus now with parametrics. In particular, we're going to talk about first and second derivative, arc length, and surface area. So we will be returning to similar formulas that we did before in Math 150, but the good news is they're actually a little easier, oddly enough, with parametrics, or not really oddly enough, you'll see why. So let's first talk about the idea of tangent derivative and second derivative. So again, parametrics are defined in terms of some other parameter. Let's talk about t. So x is in terms of t, y is in terms of t. So the derivative, dy dx, right, as always, is going to just be dy dt over dx dt, because y and x are both in terms of t. Of course, provided the bottom is not 0. A horizontal tangent is when the top is 0. Vertical when the bottom is 0. The second derivative is a little strange, so just be careful. So this is just notation for the second derivative. Notice that the second derivative is also a fraction, but it's actually the derivative of the first derivative with respect to t, right? Because dy dx, if you have a parametric, is going to be, because y and x are both in terms of t, this is going to give us something in t. Okay, that's the first derivative. The second derivative says differentiate this, that's the top of the fraction, and then divide by dx dt again. I'm not going to get into the reason why. You can look this up if you want, but let's just leave it at that, and we'll practice with one or two of these. So let's find the slope and concavity. Of course, slope is first derivative, and concavity is second derivative, specifically the point 2, 3. Okay, so 2, 3 is obviously listed as an x and a y, not a t. So you're going to have to figure that out using either of these. Again, right, it's dy dt over dx dt. So if you want, you can rewrite y as t squared over 4 minus 1, right? And so, of course, y prime then, with respect to t, is just going to be 2t over 4, or t over 2. And then x prime is, of course, 1 over 2 root t. So you put one over the other and simplify, and then you'll get that. So that's our first derivative. How do I know the slope is 8? Well, because if x is 2, that makes t 4. Okay, and you can use y also, it doesn't matter. If y is 3, t is still going to be 4. So that gives us the slope. Now the concavity is going to be the second derivative, which means what? You take the derivative of this, that's upstairs, right? That's where this comes from. And then you divide by dx dt, which is this again. Again, simplify that, you get 3t. So when t is 4, it's the same point. You get 12. That's positive, so it's obviously concave up. Okay. So it's just a matter of mainly remembering the formula for the second derivative. Arc length, if you recall from before, right, was the 1 plus the derivative squared. And that was based on the distance formula. It's the same thing, except instead of having to mess around because of x and y, and we wanted all 1 or all, all x or all y before, since everything's now in terms of t, you can leave it as is. So it's a little simpler. So basically, the arc length is the square root of dx dt squared plus dy dt squared. And it's always dt, because x and y are both in terms of t. I wouldn't worry about this. Like it says there, that's a technicality. So let's find the length around the unit circle. Right? Here's the unit circle, and t goes from 0 to 2 pi. So I need dx dt, which is obviously minus sine t, and I need dy dt, which is obviously cosine t. And then I'm going to square both of those under the radical, but of course this is just 1, and the square root of 1 is 1, so it's just the integral of dt, which is just t from 0 to 2 pi, which is 2 pi. Y as expected, because the unit circle is circle of radius 1, and of course we're talking about the length around it, which is the perimeter of a circle, right? Which you know the formula for. So you can check that with the formula, of course, but here's a demonstration of how to do it in terms of parametrics. And then our last example is a surface area. So again, this was the two options depending on rotation, remember? If you rotate it around the x, then the radius was y, so it's 2 pi y ds. And then, of course, the opposite for rotation about the y-axis. However, You don't really have to worry about choosing the ds like we did before. Why? Because it's all in terms of t anyway. So it actually makes it much easier. So let's find the surface area by rotating this parametric equation about the y-axis. So clearly we start with the 2 pi x ds. X again is 3t squared. It's already in terms of t, so it's no problem. This is going to be the ds. So x prime is 6t. We're going to square that. And then this is 6t squared. We'll square that. So this is what goes under the radical. Okay, after I factor out a 36t squared. Notice that I factor this all the way out of the radical, and it becomes 6t. That's where that comes from. This is my x, right? It's 3t squared, and that, of course, is the 2 pi. And the 0 to 5 is given. We do a little bit of combining and simplifying, and it's a straight up u sub, right? So u is, well, I guess it's not a straight up u sub. I mean, there's this extra t squared. So if u is 1 plus t squared, then du is 2t dt. So that's taken care of there. And then what do I do with the t squared? Well, if u is 1 plus t squared is u minus 1. So notice, too, that I did what? I changed the bounds here just to make life easier. T is 0, u is 1 plus 0 squared, or 1. T is 5, u is 1 plus 5 squared, or 26. That way I don't have to go back. And this is what you'd end up getting. This is the surface area. So again, they're very similar to the formulas that we had before, but I think they're a little bit easier, a little more streamlined, because everything's basically in terms of t. So here, equation of the tangent line, right? Just going to find the slope, first derivative, length of the curve. We just did that formula. Surface area, again, we just did that. Similar for the homework. Please, when it says set up only, don't try and solve it. Just set it up.